Now start with equipotential surfaces, chapter 2nd, electrostatic potential and capacitance. Part 2nd, equipotential surfaces. A surface at every point of which potential due to charge distribution is the same. Means at every point the potential due to charge distribution is same. First, for uniform electric field, in uniform electric field we have plane equipotential surfaces like V1, V2, V3, and we have electric field. For single charge Q, the potential is V equals to 1 by 4 pi epsilon naught dot Q dot divided by R. For an isolated charge, we have spherical equipotential surfaces and electric field. Now some properties. First, no work is done in moving a test charge. Means test charge में move करते time work is not done from one to another and equipotential surfaces. That means Vb minus Va equals to delta V, which is equals to omega AB divided by Q naught. If A and B on the equipotential surfaces, then Vb equals to Va. That means if 2 points A and B both are on equipotential surfaces, then both equations Vb equals to Va are same. That means Vb equals to Va. Therefore, W AB divided by Q naught equals to 0 or omega AB equals to 0. Electric field is always perpendicular to element di of the ES. Since no work is done on ES, ES means equipotential surface, WAB equals to minus integration A to B E dot di equals to 0 because, that is E dot di cos theta equals to 0. As if E not equal to 0, di not equal to 0, cos theta equals to 0 or theta equals to 90 degree. 2 ES cannot intersect. ये क्या आपस में 2 intersect नहीं कर सकते. ES indicate regions of strong or weak electric field. Electric field is defined as the negative potential gradient. So therefore E equals to minus dV upon dr. dr equals to minus dV upon E. Since dV is constant on ES, so dr directly proportional to 1 by E. If E is strong, dr will be small. Now electrostatic potential energy the work done in moving a charge Q from infinity to point. Moving a charge Q from infinity to that point in the field against the electric force is called electrostatic potential energy. First, of a two charge system. For two charge system, we have 2 point A which is held on Q1, B at Q2 and position vectors R1, R2, origin O, plane X, Y and Z, and we have between A and B R2 minus R1 vector. Here U equals to 1 by 4 pi epsilon naught Q1 Q2 divided by R2 minus R1 or 1 by 4 pi epsilon naught Q1 Q2 upon R12. For three charges system we have 1 by 4 pi epsilon naught common on the threes here, here and here. For 1 and 2 Q1 Q2 divided by R2 minus R1. For 1 3 Q1 Q3 R3 minus R1 and for 2 3 Q2 Q3 R3 minus R2. Taking common 1 by 4 pi epsilon naught common Q1 Q2 divided by R21, Q1 Q3 divided by R31, Q2 Q3 divided by R32. And for n charges we have Q n divided by R n. Now, behavior of conductors in electrostatic field. In electrostatic fields, we have net electric field intensity. Net electric field intensity in the interior of conductor is 0. interior of conductor is 0. We have sigma minus sigma, positive charges, negative charges. E sigma equals to sigma divided by E naught. Here for metallic sphere in electrostatic field, E inside 0. We have negative terms and positive. Sigma minus sigma, negative charges and positive charges. So net electric field intensity interior of a conductor is 0. Electric field just outside the charged conductor is perpendicular to the surface of the conductor. Net charge in the interior of a conductor is 0. So phi equals to integration S E dot ds equals to q upon epsilon naught. Charge always resides the surface of a conductor. Electric potential is constant for the entire conductor. So dV equals to minus E dot ER. Next, surface charge distribution may be different at different points. So sigma equals to Q by S.